Hello, welcome back. In this video session, we will derive the stiffness matrix for 1D element for conduction problem by using the global coordinates shape functions. Okay, these are the shape functions which are derived from the global coordinate systems. N1 is equal to x2 minus x divided by LE, N2 is equal to x minus x1 by LE. These are the shape functions in terms of global or Cartesian coordinate systems. And T is equal to N1 T1 plus N2 T2. That is, to find the temperature at any point, then we can use the shape functions and the nodal temperatures. So it is already derived. B is equal to strain displacement matrix, that is thermal strain and displacement are the nodal temperatures. Okay, dt by dx, okay, differentiation of this can be written as dt by dx is equal to dn by dx. It is in terms of global coordinates or the Cartesian coordinates. We know that here it is nodal temperature. Nodal temperature is expressed as the shape functions and the nodal temperatures. Okay, that is T1 and T2. This is not nodal temperature, it is temperature at any point P. Okay, so differentiating this, we have dt by dx equal to dn by dx into Q. So dt by dx, it is nothing but the strain, that is equal to, it is in terms of nodal temperatures. So this constant of proportionality, it is called as the matrix which connects strain and nodal temperatures, that is strain displacement matrix. So let us consider this B is equal to dn by dx. It is the strain displacement matrix. Displacement means it is nodal temperatures. Dn by dx. For this problems we have two nodes. For two nodes we have two shape functions, so it is taken as d1 by dx, dn2 by dx. We already derived n1 is equal to x2 minus x by LE, n2 is x1 minus x1 by LE. So substituting this n1 and n2 values and differentiating with respect to x. What is the differentiation of this term with respect to x? It is only x here, so it is minus 1 by LE, minus 1 by LE. Differentiation of this term, it is x by LE. Differentiation of this is 1 by LE. Okay, this x1 it is constant, so it is 0. Differentiation of this x1 is 0. Differentiation of this x is 1, so 1 by LE. 1 by LE. So B is equal to 1 by LE minus 1, 1. Okay, this strain displacement matrix, again it is same as that of the strain displacement matrix derived from the natural coordinates. Here also it is 1 by LE minus 1, 1. Okay, in the strain energy equation, if the nodal displacement values are removed, then it is the stiffness matrix. Substituting this B value and BT value, B value it is 1 by LE minus 1, 1, and this BT it is transpose of this matrix 1 by LE. Now it is column matrix. D it is thermal conductivity for the conduction problem, and it is one dimensional problem, so dV elemental volume can be written as A into dx. So 1 by LE, 1 by LE, it is 1 by LE square. The product of these two matrices, it is 2 by 2 size matrix, 1 minus 1 minus 1, 1. Differentiation of dx, okay, the element which varying between 0 to L. So the differentiation of this integration of this dx, it is x, then applying the limits L minus, applying the upper limit it is L, applying the lower limit it is 0. So integration of dx with respect to 0 and L, it is L. Okay, L divided by LE square is there, so 1 of the L get cancelled, so AK by L, 1 minus 1 minus 1, 1. Okay, again we have the same stiffness matrix for the conduction problem. Okay, it is in terms of global or the Cartesian coordinate system. Okay, we have got the same stiffness matrix by this method also. Okay, thank you very much.